let's say that all we're told about our situation is that we have an element that has a half-life of 3 days. An element has a half-life of 3 days. And maybe I'm responsible for coming up with that growth or decay model for that element. So the first thing I need to know is I need to make sure that I understand what the half-life of an element is. Okay, the half-life is an amount of time, and specifically it's the amount of time until half of whatever you started with remains. So if you start with 10 grams, it's the amount of time until there's only 5 left. If you start with 2 grams, it's the amount of time until there's only 1 left. Now, while it goes against a lot of students' intuition, we don't have to know how much we started with to find the half-life or the doubling time of a population. It doesn't matter whether I am shrinking from 10 to 5 or 2 to 1 or 5 million to 2.5 million. That amount of time is going to be the same. That's the beauty or the interesting part of our exponential functions. So the thing they tell us is that our half-life is 3 days, and 3 days is a time. So I know that the time that it takes for this to happen is 3. Now again, I don't know how much of this element I'm starting with, whether it's 1 gram or 1 pound or 95 kilograms, but I do know that after 3 days that only half of it is left. As long as I know the relationship of the final amount to the initial amount, I can find that missing piece up here in the exponent. If I'm given time, I can find the growth or decay rate. If I'm given k, then I can find the time. Because in the very next step, the next thing that we're going to do when we're trying to solve for that exponent is we're going to divide both sides by that coefficient. So all we have left is 1/2 equals e to the 3k. Now from there, we can take our natural log of both sides. And natural log of e to the 3k power is just going to be 3k. So we'll divide both sides by 3 and find out that k is equal to, calculator went off, negative 0.231. Alright, so once we know what k is, we can write that general equation for that element. Okay, whatever we start with times e to the negative 0.231t. So maybe the next thing, on this, maybe the next thing we're asked then is maybe we're asked the question, if we start with 9 grams of the element, how long until only 5 grams remain? Okay, so this time we were given an initial amount. It says we are specifically starting with 9 grams. And so that 9 grams goes into the y sub 0 spot. And it says, I want to know how long. When it asks the question, how long, then we know that we're solving for t. If we're solving for t, we have to know all the other pieces. And it says, how long until only 5 grams remain. So go ahead and pause the video. Solve this for t. Again, round to the nearest tenth, please. And turn the video back on to see if you're... So we said we want to figure out how long until only 5 grams remain. I'm going to try to scroll down and not make you too dizzy. Don't forget we have to divide out that 9 first to keep things as concise as possible. And then we take the natural log of both sides, which on the right just leaves the exponent. When we divide then both sides by negative 2.31, we do not get a negative time. We get a positive time of 2.5 days. Okay, some indications that you've made a mistake when you're doing these problems. Okay, if you do ever get negative time, then maybe you did what I did and you left a negative sign off of something when you divided. Okay. Or maybe you have something here upside down. The thing again that I want to warn against is, remember, if this decimal goes on forever, which 5/9 does, don't call that 0.5 or 0.55 or 0.555, and of course it would round to 0.6. You're going to be off by enough here that I'm probably going to take off a point or two. Okay, the error can get very large very quickly, and so let your calculator do this for you. There's no reason to try to stop here in the middle. It can do natural log of 5/9 as simply as it can do 0.5 or 0.55 or 0.6 or 0.56. Okay, any of those things that a lot of you would pick to put in there. Okay, so leave it as a fraction, don't write it as a decimal. Okay, let's do one more. Okay, so here is a word problem. If you need to pause it to write it down, go ahead and do that. But we know the starting population of a city in 2015. We know when we see the word continuously, that just means it's going to follow our formula that we've been working with. And in the past 5 years, in 2020, it has a population of 5.7 million. We want to find the equation to start out with that represents the growth of this population. This is our model that we start with every time. Hopefully, as we are looking at the pieces of information that we're given, we can fill in one or more of those parts. So if we start looking at some of the key values that we have the 4.3 million, we have the 5.7 million, and we have these 2 times. When they give us a starting amount, a starting time period, the 2015 is going to represent t equals 0 for us. That's when we started this experiment, when we started recording the data, whatever. So the 4.3 is going to go in our initial amount. It grew continuously, which is our E. We don't know the K. If t equals 0 is 2015, that means the year 2020 would be t equals what? If t equals 0 is 2015, then t equals 1 would be 2016, and 2 would be 2017, and so on. So 5 would be 2020. And we know the output population after those 5 years. From here, now we can find K. If I can write on my tablet, we can find K. When you find your value for K, go ahead and round, if you would, to 3 decimal places. K should be a positive number because our population is growing. It got bigger between 2015 and 2020. Okay, so use your logarithms, find your K, and then we can write down what that model is. Then we'll ask another question. Alright, so first we divide both sides of our equation by 4.3. Then when we take the natural log of both sides, all we have on the right side is the 5K, and we have natural log of that ratio on the left. We don't care what that decimal is, good, bad, or ugly, our calculator can do it. And then, I'm having issues apparently this meeting, we divide both sides by 5 to get the K. Rounded to 3 decimal places, we have 0.05637, so the 3 means leave the 6 and 6. Okay, that means now for our growth model, maybe I'll write it in blue so we don't lose our place. We know we started with 4.3 million. Okay, if it asks me for that growth model of a population, I'm always going to fill in the initial value if possible. If not, I can leave it y sub 0. And I need to know my K. T stays T. These are functions of time. When I plug in a year, it should spit out the population. From here, now let's ask a question. Okay, if the population continues to grow at this same rate, what will the city's population be in the year 2027? can make this just a little bit smaller so we have room to write. Alright, so now I know what my equation is. And if t equals 0, since I've scrolled out, I'll write it over here, represented the year 2015. We know t equals 5 represented the year 2020. Think for a minute what year 2027 would be. Okay, it's going to be 12. So now I'm back to not needing my logarithms. I'm just computing with the help of my calculator. If I plug in 12 for t, type in the numbers, it should give me a number bigger than 4.3. It should be bigger than 5.7. Go ahead and pause the video, plug it in, and see what you get. My calculator tells me it will be 8.42 million people. Which is actually almost double, which means our doubling time is just a little bit more than 12 years, actually. Okay. So we don't have to know, I'm trying to hurry because I'm about out of time. We don't have to know the actual initial amount of a population to determine what its growth or decay rate is. As long as we know how the final amount relates to the initial amount, or we know after a certain amount of time, two different populations like we did here, okay, that's enough information for us to find the K and to go from there. Okay, please contact me if you need to see more of these. If I have time, I'll throw out another video, but I'm not sure I'm going to get that done. So get a hold of me if this isn't enough.